There are three flavors of fancy factoring that we're going to try on these trigonometric expressions. The first one we're going to do is called difference of squares. And you likely remember doing this in your last course, just not on trigonometric expressions, difference of squares. So the idea behind difference of squares is that if you take a bracket with something in it plus something else, and you multiply it by a bracket containing the exact same things, except the second one is subtracted, when you do that expansion, right, FOIL or whatever you want to call it, x times x gives you an x squared. X times negative y is a negative xy. X times y is a positive xy. Y times negative y is negative y squared. And what you end up with is these cross terms undo each other because one is positive and the other is not, leaving you with x squared minus y squared as your finished expansion. So if we flip this idea around, if I see something like sine squared alpha minus cos squared beta, this is what I have here. I have a thing squared minus some other thing squared. Do you see that? So when I go to fancy factor this using difference of squares, and so difference just means subtraction and squares means two things that are squared. If I go to use difference of squares on this, it's going to end up creating two brackets, both of which contain a sine alpha and a cos beta. Written that bigger. One of them will be a positive, one of them will be a negative. Done. That thing is factored. So you can do this if there are numbers in front as well. So if I were to give you another example here, let's try and factor 9 tan squared alpha minus 16 cos squared beta. So that's a thing squared, that's a thing squared. These numbers even are squared. So I'm going to go and I'm going to write my brackets. Now it was okay when the tan was there. So I've got a tan squared and a cos squared. So I'm going to end up with a tan and a cos in these brackets. So I'll just pop them in, cos beta, tan alpha, and cos beta. Now you notice that when it was sine squared, that's 2 powers of sine. One ended up in this bracket, one ended up in that bracket. Tan squared, one part is here, one part is there. I have to split this 9 like a square. And 9 happens to be 3 times 3. So the number that goes in here is 3. And the number is there. 3 tan times 3 tan is 9 tan squared. Back here, to get 16, that would be 4 times 4. 4 cos b times 4 cos b is 16 cos squared b. And to finish this off, I need 1 to be positive and I need 1 to be negative. You can even get away with this even if the numbers are not perfect squares. So I could do something like 5 sine squared beta minus 8 cos squared beta. And when I go to factor that using difference of squares, look, I'm learning. The brackets are getting longer each time, except that one. I'm going to have to split the sine into each bracket, so I'll do that, sine beta, and split the cos, cos beta, cos beta. I'm going to have to ask myself, what times itself gives me 5? Well, that's not a clean number. It's going to be some awful decimal. And I'd put it in the calculator by doing the square root of 5. And it would spit out that awful decimal. But save yourself some energy. Just write that. Square root of 5. Square root of 5. And here would be the square root of 8. And to finish, one is positive, one is negative. All right. Last example, just to point something out to you. Cos to the power 4. No, I'm gonna clean the board off, and then we're gonna do that one because I'm gonna need some more space. Now those are power 4s. They're not power 2s, but cos to the power 4, cos 4x, is the same as cos squared x squared. So that is a thing squared. It's double squared actually. So I'm going to write it that way just so you can see it. So if I was going to factor that into two brackets using difference of squares, I would write the first thing in each bracket, and then I would write the second thing in each bracket, and then to finish my difference of squares process, one needs to be positive and the other needs to be negative. So that thing has been factored. And if you check it, cos squared times cos squared is cos to the power 4. Sine squared times sine squared is sine to the power 4. And because I have a mismatch on the signs, my cos squared sine x and my sine squared x cos squared x, one will be plus, one will be negative, so the cross terms go away. So that factoring is complete. Last little thing you might notice is that cos squared plus sine squared happens to be one of the Pythagorean identities, which you maybe saw last year. Cos squared plus sine squared happens to be worth exactly 1, regardless of what these arguments are. So this thing reduces a little more. 1 times cos squared x minus sine squared x is just cos squared x minus sine squared x, which is itself another difference of squares. So I can do this again in order to further factor it. 2 new brackets. Put my cos in each bracket. Put my sine in each bracket. 1 is plus, 1 is minus. So there we go. So what I've just shown there is that cosine to the power 4 minus sine to the power 4 is the same as cos x plus sine x, cos x minus sine x. And this is the type of thing that we're building to at the end of this chunk of the independent study, is being able to take something that's gross and prove that it's equal to something that's a little less gross. So the next flavor of special factoring we're going to do is just a simple trinomial. You did this kind of factoring for sure in grade 10 when you were doing quadratics. This is going to break up into two, actually, let's skip steps here. I'm going to try and split this central term into two things that add to 5. And the two things that add to 5 also have to multiply to 6. Maybe you remember doing this. So if I do x squared plus, let's see, 2 times 3 is 6, and 2 plus 3 is 5. So that would be x squared plus 2x plus 3x plus 6. Notice that these two terms both have an x in them. So if I factor that out, and these both have a 3 in them, and then these both have an x plus 2, then I've split that trinomial into two binomials that if you did the expansion, it would give you the same thing. So x times x is x squared. X and 2 is 2x's. 3 in x is 3 x's more for a total of 5 x's. 3 times 2 is 6. So you get the same thing back. So as the message here and all this factoring stuff is, if I replace that x up there with a cos alpha, it doesn't change the factoring process. It just changes what your variable is. So if I were to pop that up there, cos squared alpha plus 5 cos alpha plus 6, I'm just looking for two numbers that multiply to 6 and add to 5. We already figured out that that was 3 and 2. So my first bracket would get one of these cos alphas, the second one gets the other, and the numbers that multiply to 6 and add to 5 are plus 2 and plus 3. So I've got my factoring done there. I'll erase this and we'll try another one. So allegedly, there will be two numbers that multiply to 40 and add to negative 3. So you have to start making a list of things that multiply to negative 40. So the best way to do it is to start with 1. 1 times 40, 2 times 20, 3 times, 3 doesn't go evenly, 4 times 10, 5 times 8, 6 doesn't go, 7 doesn't go, 8 goes, but I already have that. It's 8 times 5. So once I've looped, I know I have the full list. In order to get negative 40, one of these things is negative, the other is positive. So I just have to look for the combination that are 3 apart from each other. That's this one. So if I split this up into a sine alpha, a sine alpha, one of these numbers is 5, one of them is 8. If I made that one negative, negative 5 and 8 would be positive 3, so that's not going to work. Positive 5 and negative 8 would be negative 3, so that's the way I'm going to go. So I've got that one factored. Just one more example for completeness. Cos squared alpha minus 5 cos alpha plus 4. So I need two numbers that multiply to 4 and add to negative 5. So things that multiply to 4 would be 1 times 4, 2 times 2, 3 doesn't go evenly, 4 I've already got, so I've got the full list. In order to get a positive number back here, they're either both positive or they're both negative. So if they're both positive, 1 and 4 would be positive 5. That's close but not quite. 2 and 2 would be 4, so it's definitely not that one. I want this to be negative, so if I did this, negative 1 times negative 4 is positive 4. Negative 1 plus negative 4 is negative 5. So those are my numbers. Cos alpha, one of them is negative 1, one of them is negative 4. Now if this happened to be equal to something, if it happened to be equal to 0, then I could set this up and do cases. I would do this is equal to 0, that is equal to 0, and off I go and solve them. There's one more fancy flavor, and then we're off to the practice problems. So one like this looks a lot like the simple trinomial factoring, except it has a coefficient in front. The simple factoring ones always had, it just said cos squared or sine squared or whatever. There was no number out there. So to do this one, you need a trick called decomposition. So the first thing you're going to do is you're going to look at the first number and the second number and you're going to multiply them together. So 6 multiplied by negative 2 gives you negative 12. Okay. Now, I need to make a list of things that multiply to this particular number. So if I go through, I could do 1 times 12, I could do 2 times 6, I could do 3 times 4, 4 times 3, but I already have that. From this list, I'm going to choose the values that add up to that number there. So I have to get 1. in order for this to be negative, one is negative, the other is positive. So I'm just looking for the one that's one apart. It's going to be this one here. If I had plus 4 and negative 3, those add to 1 and multiply to negative 12. So I'm gonna take this central term, cos squared alpha, negative 2, those were already there. I'm going to split my plus 1 cos alpha into a subtract 3 cos alpha and a plus 4 cos alpha. Now, why on earth would you do that, you might ask? Well, if you notice, in this half, both of these things contain a 3. And if I take that, oh, they have 3 and they have a cos alpha. So if I pull that out of this term, I'm left with 2 cos alpha. And if I pull it out of this term, I'm left with just the placeholder. You notice that these two both have a power of 2. And pull that out. Pull 2 out of this, leaves me with 2 cos x and a minus 1. And lo and behold, these two brackets are the same. So if they both contain a multiplication by 2 cos alpha minus 1, then I can pull that out. Leaving a 3 cos alpha in this term plus a 2 in that term. Now again, if this thing was equal to 0, you would set it up as case 1, case 2, either 2 cos alpha minus 1 equals 0, or 3 cos alpha plus 2 equals 0. And then you would solve accordingly using cast rule, either for special triangles, which this one will generate, or for not so special angles, which this one will generate. You should take a minute to try those solutions just to practice your cast rule skills. Once you get to the practice problem, it's going to ask you to do it anyway. So give that a try, see how it goes.